Hello, AP Statistics students. This is a video walkthrough of 7.7 L'Hopital's rule and indeterminate forms. There are two parts to it. One is recognizing when something is in indeterminate form, and the other is when and how to use L'Hopital's rule. The first thing here is a couple examples in our textbook that go through indeterminate forms. You should notice that both of these first two problems we could solve from what we did in chapter 1, that you can use algebra to reduce this down and figure out what the answer is. And that's what he's showing here is the algebra. Just factored it out and canceled the common factor, and then you got something that is not indeterminate. And both of these do this in a slightly different way, but that is using algebra to change the problem to something that we can solve. Even though they are in indeterminate forms, which we'll talk about later, you can still use the algebra. That means that both of these problems you could also do with L'Hopital's rule. L'Hopital's rule requires that it be an indeterminate form. The third example is actually just like this first one right here. So you factor out the 2 and you get x squared minus 1. Well, this is just a hidden form of like x squared minus 1. So it really is very similar. They factor it and then cancel the common factors, and then you can do direct substitution. The fourth one here, that is divided by x, you cannot algebraically simplify that. You can try and split it apart, but you still have something that you can't figure out. You still have another indeterminate form. So I do want to talk about that because there's been showing up here, these little things, the 0 over 0 and the infinity over infinity.
Okay, so our PowerPoint, I'm probably not going to post this for you guys because there's not much in here, but I listed out a whole bunch of different forms. Some of them are determinate and some of them are indeterminate. And you have to think a little bit to figure out which ones are which. So understand that when this says 0 plus 0, it's not really 0 plus 0. It is something that has a limit that is 0 added to another function that has a limit that is 0. And you're trying to add those together and see what you actually get. And the way you want to think about this, like our first one here, infinity plus infinity, well, as infinity is really just a big number, if you take one big number and you add another big number to it, you get another big number. There's no question about that. So that is determinate. We know it's getting just bigger and bigger. However, on the second one, if you take a big number and then subtract another big number from it, well, it depends. If the first number was bigger than the second number, you would get a positive value. If they happen to be equal, you get 0. And if the second number is bigger, then you end up with a negative answer. So you actually can't tell what that is going to equal. So that is indeterminate. So we don't know what that could possibly equal. That doesn't mean that you can't solve problems like that. It's just that you can't tell just by subtracting the limits from each other. When we do infinity divided by infinity, well, let me see. If I take a big number and divide it by a big number, well, here again, it depends on which one is bigger. If the numerator is bigger, you get something bigger than 1. If they're the same, you get something that equals 1. And if the denominator is bigger, you get something that is less than 1. So again, that's indeterminate. When we get to a multiplication, well, I guess you know now, it's determined, because a big number times a big number is just always a big number. What about a big number to a power of a big number? Does it matter which one is bigger? Well, no. It's just getting bigger. When we add small numbers, so think of 0 as just being small numbers, but I add two small numbers together. Doesn't matter how small they are. I'm still getting a small number. But again, if we subtract, here it depends on which one is smaller, or if you want to say, which one is bigger. So that's another indeterminate. And 0 divided by 0, again, just like the infinity, it depends on which one is smaller. They're small numbers, but it still depends on which one is smaller as to what you get. So that's indeterminate. Multiplying small numbers, you take a small number and you multiply it times something, it gets smaller. It doesn't matter which one it is. So we do know that that's going to just keep getting smaller and smaller. 0 to the power of 0. So, well, let's see. Shouldn't that just be 0? I mean, if you repeatedly multiply 0 by itself, you get 0. But then again, anything to the power of 0 is 1. I guess that means we don't know what it is. That's indeterminate. We can't figure it out. 0 times infinity. Well, if you multiply by 0, that is, if you multiply by small numbers, that makes things smaller. But if we multiply by big numbers, that makes things bigger. So which is it? We making it smaller? We making it bigger? It depends. It depends on which one is either too small or too big. So that's indeterminate. 1 to the power of infinity. Again, 1 multiplied by itself is just 1. So this could equal 1. Except it's not really 1. It's a limit that equals 1. So if you have numbers that are approaching 1, they're not quite there, but they're approaching, but they're smaller than 1, and you multiply them by themselves over and over and over again, it keeps getting smaller each time you multiply it. And you're doing it a whole bunch of times. So that means it could actually be getting smaller. So it could be like approaching 0 or some really small number. But if you're approaching 1 and it's actually a little bit bigger than 1, now every time you multiply it by itself, it's getting bigger. So it would be bigger than 1. So that's indeterminate. We don't know which it is. A big number to the power of 0? What do you think? Big numbers multiplied by themselves are always bigger, except if you think of an exponent that is close to 0, that's like a root or a radical, like the square root of a big number is actually smaller than the original number. So it could be getting smaller. But is it going all the way to 0? I don't think it's going all the way to 0. Is it approaching 1? I don't think so. Again, anything to the power of 0 is 1. But it depends on which one is bigger, the 0 or the infinity. So that is undetermined or indeterminate. 0 to the power of infinity. Let me see. Small numbers multiplied by themselves over and over again get smaller. Does it matter whether it's doing it a whole bunch of times? I don't think it matters. I think anytime you multiply a small number by itself, it does just get smaller. Goes to 0. So these are not actually listed in the textbook. You just there is a little mention at the end of the chapter about indeterminate. But you notice some of these are actually determinable. So the thing about L'Hopital's rule, which we're going to get to next, is that it has to be one of these two types. That is a quotient. And we have some others over here that are also indeterminate. And you can use L'Hopital's rule on them. You just have to kind of mess with it a little bit. So I want to go back to the textbook. Okay, well, here we are, back at the textbook. The next section jumps us into L'Hopital's rule.
Okay, L'Hopital's rule. If you have a function that you are trying to find the limit of that is of an indeterminate form, so we have 0 over 0, or we have all of the infinities over infinities. Sign doesn't matter. You can do negative infinities, top or bottom, or both. But it has to be of a quotient, something over something else. If it's of that form, then you can use the derivative of the numerator and the derivative of the denominator. It's actually really handy because sometimes when you take a derivative, things get simpler. Sometimes, not always. So, the first problems that you have on your assignment, problems 1 through 6, are actually of this form. They're either a 0 over 0 or an infinity over infinity, or maybe one of the positive or negative infinities. So you can actually just use L'Hopital's rule straight away. Some of them you do not have to use L'Hopital's rule, but there's a one in there with a square root that I would probably just multiply by the conjugate and do it the old way, because I think that derivative is more complicated. But you can do, I believe all of them, you are allowed to use L'Hopital's rule. So I did want to go through this real quick. It's pretty straightforward. Here we are. The first thing you have to do is check that you can use L'Hopital's rule, because it has to be of this form. So you have to think. So x is going to 0. That means this would be e to the power of infinity. No, e to the power of 0, which is 1. So 1 minus 1 is 0. And on the bottom is x goes to 0. So yeah, this is 0 and 0. This is what we mean by the 0 over 0 form. And you do have to check. If you're doing an AP test, You don't necessarily have to write all of this down, but you should verify that you have checked L'Hopital's rule. A lot of times you'll just see people do a little arrow and then write 0 and a little arrow and write 0, and that works fine. It's kind of a shorthand for all of this, but you do have to verify that you have checked that. So then he's going to apply L'Hopital's rule. So here's our original problem. This first step, most people don't write down. It's just saying that we're going to do the derivative of the numerator and the derivative of the denominator. This is not the quotient rule. You are separating it into two different problems. And here, the derivative of the numerator, well, let me see, we do e to the 2x times the derivative of the 2x. That's where the 2 comes from. Of course, the derivative of 1, or negative 1, is 0. Then in the denominator, the derivative of x is just 1. And you can simplify it if you want to. In this case, you can, once you have the derivative, do direct substitution. That's e to the 0, which is 1, times 2, gives you 2. Piece of cake. Really handy. The difficulty with L'Hopital's rule is not applying it. It's realizing that you should apply it. That you can, in this unit, as we're going through, you know you're doing L'Hopital's rule. It's when you're on a final exam or an AP exam, and there's nothing that says use L'Hopital's rule. So here's a second example, very similar. We should verify that it is of the right form, but as you let x go to infinity, well, the natural log of big numbers is a big number, and then of course that's infinity, and then just letting x go to infinity is infinity. So again, they just do the derivative. Knock that off. They just do the derivative of the numerator and the derivative of the denominator. So most people would not write that step, but the derivative of the natural log of x is 1 over x, and the derivative of x is just 1. So then you can do direct substitution. So you actually end up with 1 over infinity, which does equal 0. Easy peasy. Okay. Example 3 is very similar. This is, well, let's see. Knock that off. X squared, as x goes to negative infinity, x squared is going to go to infinity. E to the negative, big negative number, that would be e to a positive number, would go to infinity. So it is infinity over infinity. You have to think about that before you apply L'Hopital's rule. So then did the derivative, boom, boom, and, well, you can't figure that one out either. But that's okay, because now on this last part, if we let x go to negative infinity, well, we get negative infinity. 2 times a big negative number is a big negative number. And negative e to the positive, big positive number, because minus a negative, well, that would give you negative infinity. So we have negative infinity. Oh, we can use L'Hopital's rule a second time. You bet. Hey, why not? Why not do it 2, 3, 4 times, however many times you need it? But you do have to stop. So here it is doing it the second time. You do have to stop and verify that you actually can use it. There is one example at the end of the chapter, at the end of this unit, where he presents a problem where if you use L'Hopital's rule, you get the wrong answer. This is his second use of L'Hopital's rule, and there we get finally direct substitution. You end up with 2 over infinity, which would be 0. Okay, your first, on your homework assignment, problems 1 through 6 are like this. They are either a 0 over 0 or an infinity over infinity. You just verify that you can use L'Hopital's rule and then use it.